Section 21.7, Nuclear Power, Fission. According to our discussion of the energy changes in nuclear reactions, both the splitting of heavy nuclei, fission, and the union of light nuclei, fusion, are exothermic processes. Commercial nuclear power plants and the most common forms of nuclear weaponry depend on the process of nuclear fission for their operation. The first nuclear fission was to be discovered was that of uranium-235. This nucleus, as well as those of uranium-233 and plutonium-239, undergoes fission when struck by a slow-moving neutron. The induced fission process is illustrated in Figure 21.14. A heavy nucleus can split in many different ways. Two ways that uranium-235 nucleuses split are shown in equation 21.4 and 5. More than 200 isotopes of 35 elements have been found among the fission products of uranium-235. Most of them are radioactive. On average, 2.4 neutrons are produced by every fission of a uranium-235 nucleus. If one fission produces 2 neutrons, these 2 neutrons can cause 2 additional fissions. The 4 neutrons therefore released can produce 4 fissions, and so forth, as shown in 21.15. The number of fissions and the energy released quickly escalate, and as the process is unchecked, the result is a violent explosion. Reactions that multiply in this fashion are called chain reactions. For a fission chain reaction to occur, the sample of a fissionable material must have a certain minimum mass. Otherwise, neutrons escape from the sample before they had the opportunity to strike other nuclei and cause additional fission. The chain stops if too many neutrons are lost. The amount of fissionable material large enough to maintain the chain reaction with a constant rate of fission is called the critical mass. When a critical mass of material is present, 1 neutron on average from each fission is subsequently effective to producing another fission. The critical mass of uranium-235 is about 1 kilogram. If more than the critical mass of fissionable material is present, very few neutrons escape. The chain reaction thus multiplies a number of fissions, which can lead to a nuclear explosion. A mass of excess is a critical mass is referred to as a supercritical mass. The effect of mass on a fission reaction is illustrated in Figure 21.16. Figure 21.17 shows a schematic diagram of the first atomic bomb used in warfare, the bomb that was dropped on Hiroshima, Japan, on August 6, 1945. To trigger a fission reaction, 2 subcritical masses of uranium-235 are slammed together using chemical explosives. The combined masses of the uranium form a supercritical mass, which leads to a rapid, uncontrolled chain reaction and ultimately a nuclear explosion. The energy released by the bomb dropped on Hiroshima was equivalent to 20,000 tons of TNT. It's therefore called a 20-kiloton bomb. Unfortunately, the basic design of a fission-based atomic bomb is quite simple. The fissionable materials are potentially available to many nations with nuclear reactor. This simplicity has resulted in the proliferation of atomic weapons. Nuclear reactors. Nuclear fission produces the energy generated by nuclear power plants. The fuel of the nuclear reaction is a fissionable substance such as uranium-235. Typically, uranium is enriched to about 3% uranium-235 and then to form of UO2 pellets. These enriched uranium pellets are encased in zirconium or stainless steel tubes. Rods composed of materials such as cadmium or boron control the fission process by absorbing neutrons. These control rods regulate the flux of neutrons to keep the chain reactant self-sustaining while preventing the reactor core from overheating. The reactor is started by a neutron-emitting source. It is stopped by inserting the control rods more deeply into the reactor core at the site of the fission. The reactor core also contains a moderator, which acts to slow down neutrons so that they can be captured more readily by the fuel. Graphite is commonly used as a moderator. A cooling liquid circulates through the reactor core to carry away heat generated by the nuclear fission. In some reactor designs, the cooling liquid also serves as the neutron moderator. The design of nuclear power plants is basically the same as that of a power plant that burns fossil fuels, except that the burner is replaced by a reactor core. In both instances, steam is used to drive a turbine connected to an electrical generator. The steam must be condensed, therefore. Additionally, cooling water, generally obtained from a large source such as a river or lake, is needed. The nuclear power plant design in Figure 2120 is currently the most popular. The primary coolant which passes through the core is a closed system, which lessens the chance that radioactive products could escape the core. Additionally, the reactor is surrounded by reinforced concrete shell to shield personal and nearby residents from radiation and to protect the reactor from external forces. After passing through the nuclear core, the primary coolant is very hot. The heat content of the coolant is used to generate high-pressure steam and heat exchanger. In the United States, more recent nuclear reactor designs use gas cooling instead of liquid cooling, which means fewer pipes and valves, but the basic operation principle is unchanged. Newer designs for nuclear reactors are being developed. South Africa is building a nuclear power plant near Cape Town, expected to be operational in 2010, that's based on the pebble bed reactor design that was originally conceived in the United States after World War II. In the pebble bed design, small specks of low-enriched uranium are coated with ceramics and graphite and pressed into balls about the size of an orange. These balls are pebbles and contain only a few percent of uranium. When ready to run, about 500,000 pebbles are placed in the reactor core along with the control rods. Helium gas is the coolant. As the nuclear reactions proceed, the pebbles heat the helium, and the helium drives the turbine connected to a generator. One advantage to the pebble bed reactor is that helium is not subject to steam explosions. Like water, it does not readily absorb neutrons to produce radioactive products. Another advantage is that the pebble bed reactor does not need to be shut down to add more fuel. Engineers can take some petals out of the bottom and weigh them to see if there's still usable fuel inside and add usable petals to the top of the pile. Fission products accumulate as the reactor operates. These products decrease the efficiency of the reactor by capturing neutrons. Current commercial reactors must be stopped periodically to replace and reprocess the nuclear fuel. When the fuel rods are removed from the reactor, they are initially very reactive. It was originally intended that they would be stored several months in pools at the reactor site to allow decay of short-lived radioactive nuclei. Then they were to be transported to shielded containers to reprocessing plants where the fuel would be separated from fission products. Reprocessing plants have been plagued with operational difficulties, and there is intense opposition in the United States to transport of nuclear waste on the nation's roads. Even if the transportation difficulties could be overcome, the high level of radioactivity of the spent fuel rods make reprocessing a hazard of operation. At present in the United States, the spent fuel rods are simply being kept in storage at reactor sites. However, in 2007, the federal government proposed initiatives that would allow for the reprocessing of spent nuclear fuel, overturning a 30-year ban. Russia, the UK, France, China, and Japan have already developed processing methods and sites. Storage poses a major problem because the fission products are extremely radioactive. It's estimated that 20 half-lives are required for their radioactivity to reach levels acceptable for biological exposure. Based on the 28.8-year half-life of strontium-90, one of the longer-lived and most dangerous of the products, this waste would be stored for 600 years. Plutonium-239 is one of the byproducts present in the expended fuel rods. It's formed by absorption of neutron uranium-238, followed by two successive beta emissions. Remember that the most of the uranium in the fuel rods is uranium-238. If the fuel rods are processed, the plutonium-239 is largely removed because it can be used as a nuclear fuel. However, if the plutonium is not removed, fuel rod storage must be for a very long time because plutonium-239 has a half-life of 24,000 years. A considerable amount of research is being devoted to disposal of radioactive wastes. At present, the most attractive possibilities appear to be the formation of glass, ceramic, or synthetic rock from wastes, which means immobilizing them. These solid materials would be placed in containers of high corrosion resistance and durability and buried deep underground. The U.S. Department of Energy has designed Yucca Mountain in Nevada as a disposal site, and extensive construction has been done there. However, because the radioactivity will persist for a long time, there must be assurances that the solids in their containers will not crack from the heat generated by nuclear decay, allowing radioactivity to find its way into underground water supplies. In spite of all these difficulties, nuclear power is making a modest comeback as an energy source. In 2005, there were 440 working nuclear power plants in the world, most of them which are at least 20 years old. Another 26 nuclear power plants are under discussion, mostly in Asia, and plans for more in the progress. The threat of global warming has moved to some organizations propose nuclear power as a major energy source for the planet in the future. However, this goal would require the construction of at least 1,000 new nuclear power plants over the next 50 years.